In this example here, we're asked to come up with the Fourier series for this periodic square pulse wave that we have shown there on the screen. In addition, we might talk about how a single degree of freedom oscillator might respond if this were the excitation. So the form of the Fourier series that we're going to use will be the cosine sine one. So the Fourier series here for f of t is going to be equal to f naught, the average value of f, plus the sum over all the harmonics for the cosines and sines. So that was f cj cosine j omega t plus f sj sine j omega t as that. So our task really is to find f naught, fcj, and fsj. F naught, as we saw, was equal to the average value of f. So if we look over one period from here to here, the area under the curve is going to be f naught times a. The period over which it acts is t. So that's the average value. We could do the integration. I would ask you to do so to check it out. But we're going to get that value, which is the average value of f over one period of t. The coefficient fcj, we find that by 2 over t, integral from minus t over 2 to t over 2 of f of t cosine of j omega t dt. So we recognize here that we need to really break this integration up into three parts. The first part is going to go from minus t over 2 to minus a over 2 of f of t cosine j omega t dt. Next, from minus a over 2 to positive a over 2 f of t cosine j omega t dt. And then from a over 2 to positive t over 2 f of t cosine j omega t. So really all I'm doing here is dividing that interval from minus t over 2 to t over 2 into three parts. And the choice here is that over this range, the force is turned off. Over this range, the force is turned off. Over this range, the force is held to be a constant value there of f naught. And so I think let me rewrite this as capital F naught so I don't confuse that with the average value of f. So what we have then is the need to do an integration of cosine. So this is from minus a over 2 to a over 2 of cosine j omega t dt. If we integrate cosine, we get 1 over j omega sine j omega t going from minus a over 2 to positive a over 2. And since sine is an odd function, if we evaluate it at plus a over 2 and subtract away what it is at minus a over 2, we effectively get twice one of them. So this is 2 sine j pi a over 2 divided by j omega. Therefore, this becomes two f naught times sine of j pi A over T. This is substituting in for T is equal to 2 pi over omega. So those are our coefficients, FCJ. FSJ, we don't really even have to do the integration because since f of t is an even function and sine j omega t is an odd function, when you integrate an even and an odd function over one period, you get a 0. So f of t, our excitation, f of t, is going to be a f naught over t plus 2 f naught, bring that constant there on the outside, the sum over j, 1 to infinity of sine of j pi a over t divided by j pi times cosine of 2 pi j t over t. So that is our Fourier series. So note that our coefficients there go as 1 over j. So that's going to be our first observation. So the coefficients f, cj go as 1 over j. This would be fairly slow convergence. In fact, if there weren't some sign changes going on with each term, SIGN sign terms going on here, it would not converge, but 1 over j will converge with those, but it's going to be slow. And the reason for this is f of t has discontinuities. We saw that the Dirichlet theorem says that when you have discontinuities, it will still converge, but it's only going to be converging in the average sense at those discontinuities. If this is actually a forcing, on a single degree of freedom system, let's say the single degree of freedom system has an equation of motion of mx double dot plus cx dot plus kx is equal to f of t. We know that the particular solution of that equation of motion, we can find that by f naught over k plus the sum j going from 1 to infinity here of this amplitude transfer function h times the cosine Fourier coefficients fcj cosine j omega t minus pj, where you might recall that this amplitude transfer function h is given by 1 over k square root of 1 minus j omega over omega n squared, all that squared, plus 2 zeta j omega over omega n, that quantity squared. The point being is that fcj goes as 1 over j. We see here that when you take into account the square root, this goes as 1 over j squared. So although the f of t has slow convergence. And slow convergence actually is a physical interpretation, is that the higher harmonics do not go down quickly, with J. The response does go down. It goes down as 1 over J cubed. So again, you're going to see higher harmonics in the excitation, and those are needed to make the very squareness of the wave, or at least its attempt to. But by the time you run that forcing through the filter, which is the single degree of freedom oscillator, those high frequency components get filtered out. So in conclusion here, what I would like to do is look at what we get if we try to reconstruct our forcing. So if I look back at our Fourier series for the excitation, so this is f of t is equal to f naught plus j 1 to infinity here of f cj cosine j omega t. If we recognize, we're not going to find a closed form solution for this, so to say we're going to go up to infinity is not an accurate statement. We need to truncate it. So if I truncate this after 60 non-zero terms, this is how the f of t looks. It resembles a square wave. In fact, the square wave is shown there in the blue background. The red is the 60-term approximation of the Fourier series. We see that there are oscillations which are amplified there near the discontinuities. Again, this goes back to Dirichlet's theorem that says that the Fourier series will converge only in the average sense at the discontinuities, and the fact that you put in more and more terms, those oscillations actually never die away. We keep up picking up more and more of the higher harmonics, but the oscillations there, the ringing there at the step change remains. But it still does converge in the average sense at the discontinuities. We're not really that concerned about duplicating the forcing, but we're more interested in knowing what the response is going to be. Because again, the system filters out high frequency stuff by 1 over j squared. The excitation goes as 1 over j. These higher harmonics get filtered out as 1 over j cubed in terms of the response there of xp.